Hello, it's Stat 135, Lecture 27. Last time we finished our treatment of the chi-squared test, including goodness of fit, test of homogeneity, and test of independence. Remember that a goodness of fit test is for a single sample from a population where we ask, does the population have a particular multinomial distribution? The test of homogeneity has multiple samples from subgroups of a single population and answers the question, do subgroups have the same multinomial distribution? And a test of independence has a single sample from the population, and you fill out a contingency table and answers the question, are categorical variables independent? Today, we're going to go over our in-class exercise from last time and talk about non-parametric two-sample tests called the Mann-Whitney test. So I'm not going to discuss the in-class exercise in this video. So that's at the end of the notes from last time. You can look that over. So remember that in section 11.2 we were comparing two independent samples of continuous data, and for the t-test we assumed that our data was normal and that the null said that the population means are the same. But for small sample size, often we can't assume that our data is normal, and we use a non-parametric test called a Mann-Whitney test or a rank sum test or a Wilcoxon test, all the same test. So here's an example. We test whether a diuretic works for alpha is 0.1 using a one-sided test. Two groups, we have X as control and Y as the treatment group, and we have two independent samples. The control group has sample size 3 and the treatment group has sample size 4. Our null is that the treatment doesn't work, so the control and treatment populations are the same. The alternative is that the treatment works. So it's a diuretic, which makes you pee more, so the treatment works, you pee more. So we rank daily urine production from smallest to largest, and we find the rank sum of X, the smaller group. Let's take a look at this here. So we can see the daily urine productions here, and we see that the rank sum for the control is T is 9. So here Tx is 9. So we're wondering, how extreme is this? So we find the sampling distribution for T sub X, and there are 7 ranks, and the control has 3 of those ranks, so there's 7 choose 3 different ranks that the control can have, so that's 35 equally likely rank sums of X. So here are those 35 rank sums all the way from 6 to 18. 6 would be ranks 1, 2, 3, and 18 would be what would that 4, 5, 6, 7, and so we can see that that 9 has a one-sided p-value of 7 over 35. 7 because at 9 there is 1, 2, 3, 4, 5, 6, 7. There are 7 rank sums with a there's 7 rank sums that are less than or equal to 9. And so the cutoff for alpha 0.1 is 7, and 9 is greater than 7, so we accept the null. And so we got 7 because 2 out of 35 is 0.057, but 4 over 35 is 0.11. So we have to make the rank sum 7, not 8, for the cutoff. Great. So Also, we have this table here, which gives you the critical cutoff value for t sub x. So, great. Okay. Now you could have tried to show that ty is extremely large instead of tx being extremely small. Tx and ty are related. Tx plus ty is the sum of 1 to 7, which is 7 times 8 over 2. We use tx in this problem since it's the smaller rank sum, and the table above gives the critical values for the smaller rank sum. Just a word about convention. X is the control, y is treatment, x has distribution f, y is distribution g, and we have two independent samples, x1 to xn, y1 to ym. Unfortunately, your book discusses ty, not tx. So, but tx and ty are related, so that's not really a big deal. So a theorem in the book gives you the expectation invariance of tx and ty. Remember, y is the treatment group. So for large sample sizes, actually I should be a little bit more clear. So y is the larger is the one with more ranks in it, with the larger sample size, I should say. Yes. So for large sample sizes, ty is approximately normal. So to see why, we introduce a related test statistic called the Wilcoxon test statistic, which is a sum of indicators, which is all xi, yj pairs. So x and y are the urine productions for treatment and control group here. And so these indicators are almost independent, but they're all identically distributed. So these UYs are approximately normal by CLT. How do they relate to TY? So we look at the statistic of these XIs, so that puts them in ascending order. So for example, if x1 is 2, x2 is minus 1, x3 is 0, then x parenthesis 1 is the min, and x parenthesis 3 is the max. So note that the sum of these indicators is the sum of all comparisons of x and y. So the sum of these indicators, xi less than xyj, is equal to the sum of the indicators x parenthesis I is less than y parenthesis j. And if ry1 is the rank of y of the first of the smallest yi in the combined sample, down to ryk, so that's the rank of the kth largest treatment urine production in the combined sample. So you can write that uy is the summing over all x parenthesis I, y parenthesis j, is the number of x is less than y1 plus the number of x's less than y parenthesis 2, and so on. And so the number of x's less than the first y, that is precisely ry1 minus 1, because ry1 is the rank of y1 in the combined sample, and because parenthesis 1 is the smallest y. The number of x's less than y1 is the rank of y1, parenthesis 1, minus 1. You're subtracting the y1 here. And the second one, the number of x's less than y2, is ry2 minus 2, and you're subtracting 2 because you need to subtract y parenthesis 1, y parenthesis 2. And so on. In the end, you need to subtract m. You're basically subtracting all the y's. So I think that's fairly clear. And then uy is hence the sum of all these ryi's minus the sum of 1 to m, which is m times m plus 1 over 2. And the sum of these ryi's is ty. So we get that uy is ty minus m plus 1 over 2. And so we know that uy is normal, and hence ty is also normal. So, and furthermore, you can say what the parameters are for ty, and that's what I've given here. So this uy here is called a Wilcoxon test statistic, and so it is. So to actually, so this is some number less than m times n. So uy. So essentially, remember, uy is the sum of all m times n indicators. So it's definitely going to be between 0 and 1, and it's, in fact, if you divide by 1 over m, if you divide it by m over n, you get an estimator for the probability that x is less than y, which we'll call pi. And I think that's a little bit further than we got in lecture today, but I will review the end of this at the start of next time. Have a great day.